And we have sound, excellent. So thank you so much for joining us this morning. I'm Heather Wade, I'm the VP of Engineering at Whitepages in Seattle. And I've got Varun here with me, he's the Senior Principal Architect, and Jason Frazier, who is the technical lead for the Redis on Flash implementation that we're going to be talking about today. So I'm going to talk a little bit about Whitepages and who we are and some of the problems that we're trying to solve. We're going to talk about our global identity graph, which is a graph of over 5 billion entities and links between those entities that we use to power our products. And then I'm going to hand it off to Varun, and he's going to talk about some of the specific technical challenges of storing and serving that data. And then Jason's going to dig into some of the benchmarking work that we did in evaluating storage solutions for our identity graph. And then we'll wrap it up with some of the things that we've learned, and hopefully some of that will be useful to you guys as well. So if you're not familiar with Whitepages, you might wonder what we do. We do not print phone books. We actually have a graph database of over 5 billion identity records. That would be information about people, like their names, their dates of birth, et cetera, as well as their contact points, like their addresses, their telephone numbers, email addresses, et cetera. And then all of the links between these entities and between the people and their contact points. And on top of this data asset, we have two business lines. We have whitepages.com, which is our consumer offering, and that's available, on the web as well as a mobile app, and you can use that to do things like search for a person, or do a reverse phone number search, or search for a business, or a reverse address search. So it's a tool for consumers to be able to find data about people. And then the other business unit that we have is Whitepages Pro, and that is our enterprise B2B offering. And I'll talk a little bit about those use cases here in a second. But between these two business units, we have over 50,000 unique monthly visitors. And with that, we have the challenge of our growing data sets and being able to serve low latency responses with this data. So again, I'll talk a little bit more about the Whitepages Pro use case because I think it motivates a little bit our need for a solution like Redis on Flash. Whitepages Pro is basically using our identity our identity graph data set to serve identity verification and fraud prevention use cases for enterprise customers. And these customers are across a lot of different verticals, like lending and banking, as well as e-commerce or payments and travel and hospitality. So to think about a specific example, let's say you're on Expedia.com and you're booking your tickets to RedisConf, right? And in the middle of that transaction, you give them your payment information and you're booking the trip. On the back end, Expedia is doing a lot of things. They're working with payment processors, but they're also calling, for example, the Whitepages Pro API and sending us some of that transaction data. And Whitepages Pro returns to them information about how likely it is that this person is who they say they are. How likely is this to be a fraudulent transaction versus a legitimate transaction? And then they can use that as one input into their decision-making process of whether or not they're going to flag that transaction as fraud or they're going to allow it to go through. So all of this is happening, of course, in real time as the transaction is happening on the web. And so the latency requirements for our Pro product are really critically important because not only do these enterprise customers care about identity verification and preventing fraud for their products and services, but they also care about their customers' end user experience as well. And so, we're really tasked with shaving as much latency off of these API responses as we possibly can. And Jason and Varun will get into a little bit more about that later. And then on the premium side, that was the consumer whitepages.com and the Whitepages app that I was referring to. We're serving very similar information there with the contact lookups. And then we also have some premium offerings where people can get background check information and things like that. And so powering both of these is our Whitepages identity graph. So as I mentioned, we have about 5 billion or so different entities, and these look like people with their names and all of the metadata that you would expect to see with a person, all of their email addresses, phone numbers, addresses, their businesses. And every month we process 2 billion new links between all of these entities and contact points in our graph. So I'm going to hand this off to Varun right now, and he's going to talk a little bit about the technical challenges involved in this.
Hey everyone. So can I get a quick hands-on techies or the people who are coding, or let's say still coding or love to code? Say, and how many of you are here to understand maybe Redis on Flash specifically or graph implementation? All right, so I think we have the kind of audience we want. So if you understand these entities and these little graphs here, they're showing like it is a person, his address associated with it, his phone number, his email addresses, and all of it is connected. So there is a degree of connectedness and all that theory around 3 degree and all that things hold, which makes this graph like very unpredictable in sense of it's not highly connected and it's not very sparse as well. It depends upon locality, it depends upon zip code, it depends upon a lot of things. So that's one of the biggest challenge, and we'll address how did we map it and how did we architect it so as to fit to our use cases most. So just going over these numbers a little, 5 billion unique entities, 18 billion links, around 3 terabytes of data. That is compressed. It's actually 10 to 11 terabytes of data, which if we get compression, we'll go through over it. And on average, we get 200,000 requests per second on a data store, which is Redis right now. So this is the typical data flow just to understand what's happening. All our properties, which is Whitepages, free site, or the consumer site, what we like to call, and the premium or the API, all of it is essentially we serve use cases like reverse address, person lookup. You search for Jon Snow in Westeros, and you'll get someone, maybe not. And then so that all those queries first go to a search service, which is backed by Solr, and we index only the searchable fields in Solr, because nobody wants to search on let's say, some of the person attributes like gender maybe. Maybe they don't want to search, or maybe they want. So we have certain filters, and we don't allow certain filters. Like age is allowed, and certain things like telephone numbers for a person, you cannot search with a person and a telephone together, and those kind of things. So indexable fields go into search. Before that, again, how we arrive at this data is huge. You saw the slides with our partner data. We have various data sources where there's a massive data pipeline powered by Databricks. And we get our data, process it, multiple layer of filtering and everything. It comes here. So one portion of it is indexed in Solr. And then once you do a query, Jon Snow, San Francisco, and you get a list of 10 results, 15 results as the application may be. Those are standard UUIDs and mean nothing. So we have to take those IDs and send to the identity graph to expand those into subgraphs. So a person, Jon Snow, we get his address, phone number, email, or whatever the requirements is. And then that is what you will see in the home page of the results. So if you just do the multiplications here, for one request that we get typically 15 results on the consumer side, 10 or 5 on pro APIs, depending on the customer needs. And for each of those, we have to make a subquery to get the subgraph. By the way, I know a lot of things, when we talk about it, we have been dealing with it day in, day out, so we have a lot of things in our mind, so feel free to interrupt, raise your hands. If you have any questions right now, we have a really nice group of people who are really interested, so I'll be more than happy to address anything now or offline. So now, before going into the whole database design and how we progressed and things, just want to make key requirements, which are like, there are several requirements, of course, but these are some non-negotiable requirements for us, which is mainly, as Heather was saying, that our latency is one of the prime things, and we'll explain how just the underlying data store needs to be within 1 milliseconds. We saw it in keynotes as well. There is so much of network traffic and all that. The data stores cannot be in single digits. That was last year. And it is some milliseconds now, and that's what we want it to be. Throughput, 200 requests per second. Consistency is another very big thing for us. like a couple of years back, we were mostly on consumer businesses, which was okay to be down for certain minutes of day. Nobody notices. Somebody comes and search for someone. They don't find the result. They come back again. But when we have enterprise customer, it is very, very important to be up all the time because that's an issue. That's a promise that we fail. So we want a system where if the primary node fails and the secondary is coming over and it takes 40 seconds or even 10 seconds to fail over from primary to secondary, we lose business. And we want typically saying 100% uptime, 99.9, and the 4 nines are the standard which you have to promise, and I can't say 100 here. But to my whole team, it's always 100. Multi-AZ, it's kind of like a very standard thing, nothing surprising there. This is the evolution that we went through to arrive at where we are right now. When we started our shop, like several years back, data was less, and our demand was less. Speed was not such a big concern in those days. People used to be, it was an understanding if you're going to a web page, you open a browser, you are going to wait. Especially if you give instant result, it feels like some voodoo, and we are faking, look like a fraud site, so we artificially wait also, and it was organic for us. So PostgreSQL was enough for our use case. Then we progressed because our data was rising, internet was getting more affordable, and it was growing. Anybody identify the image? Okay, no goodies with me still. Okay, no, so that's Titan, and we backed it with Cassandra. Those two the hottest technologies, brimming with great engineers in the team, and we thought that's the best way to go. And there was no Neo4j, at least I don't know if there was Neo4j at that time, or OrientDB, or a lot of fancy graph databases that have come up there. Titan, the story has been a little funny. It is great. It is greatly architected. It is of great value, and you can expand it well. But with it comes huge amount of complexity. There are a lot of magic going on. There are a lot of hidden dragons. So when something goes wrong, it's a nightmare to debug, and our whole site is down. And we just have to wait, what is happening, and then go through thread level, process level, and so many things go wrong. So what we needed was stability and simplicity, where we have complete control about how our data is structured, stored. Some regions we were getting good speed, some queries were very slow. So then we thought, okay, what is it that are we lacking? Do we really need a graph, and what level of graph we need? And that's when we thought, and we saw that if you remember the subgraph, when you talk about the typical use cases, I want to know where does this person lives, who all have lived in this address previously, and what are their phone numbers. Think of all the typical use cases. Our product and business sat together, listed on all the current and the future use cases, and we arrived at a conclusion that we do need our data is implicitly a graph database, a graph structured thing connected, but it is connected, and we can still achieve that 3-level depth that we want to go. We never want to traverse more than 3. So we don't need it to be completely connected in an implicit way. We have to optimize for what we have. So we flattened our whole structure, removed the complete complexity, and tried to map the whole data, whole graph into a key value pair. It's again going back to basics. It's more like an adjacency matrix where there is a key, which is the ID, let's say my ID, and then there are my key attributes, my age, gender, blah, 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 and then a set of links that I have, person links, telephone links, and this. All of it forming into a simple JSON structure, compressed, and that's what we have. So when our search service, in the previous slide, as you saw, search service gives us an ID, I go to the graph, query for that ID, I get the list of all the telephones and the emails for all the 10 results that have come. For all the telephones, I go a level deeper to go, if I want to have, let's say addresses, I want to go deeper to go know people who have lived before, or as the use case may be. Any questions so far? Great. Sorry.
So this graph is very similar to social graph, for example, from Facebook, right? Have you compared with what technologies they use, or you know?
Sorry, yeah. I'm just curious about like your similar of your competition or other offerings. What kind of technologies they're used? Have you looked at it?
Yep. So it's a very interesting question, and that comes up every time we talk and think. There is a subtle difference between social network and us. It is the degree of relationship. and people to people. And if you see, I can talk more deeper offline about how we do entity resolution when there are like one credit card company telling you are John Snow and one company saying John S, and how do we know are the same person and not? So person is kind of the most complicated of all the use cases, and we are lucky that humans in general, in reality, don't have that many friends or relatives. There are not 1,000 people living in the same house. There are not 1,000 siblings that you have. So we do that. So we chose to optimize in that sense. Plus then there is a sense of scale and cost, which is two biggest thing. We strongly believe in frugal architecture, which makes us simple and makes us successful. Frugality is like, can't speak more of it. Yeah, I have to say more frugality. I would like not to be, but with the VP standing next to me, I have to be saying such things. Okay, so we can talk more about it, but it's mainly around that reasoning. So as I said, yeah, please. What kind of pre-filtering do we do to get the data? Or insert it in the graph. So there are multiple layers. Like again, I'm not exactly sure if I'm going to I'm understanding your question, but it's like when we have the raw data coming in, it goes through several layers of MapReduce and several layers of ETL jobs and things all to merge, mix our proprietary logic to try to match people. If they share a contact point, same phone numbers, of course they are same person. But John Snow with a phone number, John Snow with the address, I don't know if they are same or not. Their name is exactly same, but don't know. So there is a lot of intelligence and all goes on. After it comes, still, there is huge amount of noise. Just try to go to Zillow and search for some houses. There is a house with 800 square feet, and it has some 1,020 rooms in it. So, and at Zillow. And it's kind of listed and everything and all. There is that kind of noise, and same thing for people, it happens. So it is noisy. So what we need to do is, as we are going down the funnel, we are filtering. What goes into search is only people with addresses, let's say. Like, I mean, we have all the respect for homeless people, but we don't want them to be searchable here because I don't know what address I'm going to give for him. And it's implicit that the value of what we want to give comes in from addresses or something. So it just gets filtered. Plus, if you are one of the person who is changing houses every day, so we have like 50 historical address for you. We filter it to certain limit and try to limit the graph so as to make the signal to noise ratio constant. Did I get closer to it? Okay. Okay, so we have reached Elasticache, and that's when we moved to Redis. We flattened our structure, modeled it, everything, and we were US, Canada only. And then we started growing like every other company does, and we went into international, and now I don't know exactly how many countries data we have, but like address validation, we support almost all the countries in the world. And for people and telephone and email data, we have several countries and numbers we can get it. But what happened with that is US population was not growing, at least not to the extent that I need to expand my graph. But world population, when I'm adding a new country, suddenly changes the whole equation. We added Mexico, we added Brazil, and our data is suddenly 6-folds. And we haven't even thought of starting to add China or India right now. And I don't know, where are we going to fit that then? So we needed to grow. So there are two considerations when we are considering to grow beyond the 10x or 5x level. The number one is cost, or number two is cost. Number one is, are we able to do that? Can we scale? Yes. So Elasticache, Amazon, as of some days, I don't know if it changes every day. I might have missed some update notice, but it has a physical limitation of no more than 15 nodes in a cluster. The largest node you can have is R4 8x large, limiting your whole data size to be no more than 6 terabytes, and that was less for us. We already crossed 6 terabytes, plus with replication, it was way more that we needed. We can't fit in there. Second, the cost. If you just self-host Redis on a bare metal instance or like a normal EC2 instance versus Elasticache, it is really awesome, really good, the simplest or the most beautiful service I know to get started with, very easy to integrate, but there is a cost added to it. And that cost is really small if you are on a single cluster using for a site with like a couple of hundreds of gigs, but when you're in terabytes, that cost is multiplied. The cost gets more than having 1 or 2 full-time engineers. And that was the reason we moved to Redis Labs, and I will go through some details. So just to get a little bit deeper into how our mapping of a graph goes into the flat structure, we have, again, a proprietary shape language that we use. It is more of to express, you can call it like our version of Cypher or our simpler version of the more complicated or more confusing query languages around graph. So we developed this on our own to map it to flat data structures. And it's simple. I want address. So I have an ID, which is an address. For those addresses, I want person, 5 current and 5 historical person. For those persons, I want 5 current and 5 historical links to those persons, like their siblings or any relation, person-person relation. For those persons, I need, again, addresses recursively. For addresses, I need non-addresses. Non-addresses are like an internal term, which is more like city, state, or geography and things and all it goes in. And then finally, person to person on that address. So it's completely recursive, as you see, and which is the implicit nature of a graph. And what we're able to achieve here is just express everything in a common way. And it's super, super simple to parse this compared to Cypher or anything. That gives us one more reason why we didn't want to go to any graph databases and stick with something more flat. OK, I'm going to breeze through it now a little. And we'll come back to some of the key learnings and things and all. Meanwhile, I'd like Jason to take over and go over some benchmarking. How did we choose Redis slabs instead of, or Redis, so to say, to start with, instead of a lot of the databases or key value stores that we can get? Jason.
Thanks, Varun. So as Varun mentioned earlier, because of this limit that Elasticache had, eventually we needed to find a different solution. And because of this, we went out to go look at a whole bunch of different database technologies to try and see what would fit our needs. There is a trade-off, though, in terms of cost to latency, where we could have an incredibly fast database, but it would cost a whole bunch. We were trying to get that nice middle zone of savings and not sacrificing too much on latency. So for most of our benchmarking, we used the Yahoo Cloud Serving Benchmark tool, mainly because it had built-in support for a whole bunch of different technologies and helped us kind of eliminate as many variables as possible when it came to getting our results. So the first 2 technologies we benchmarked were Cassandra and MongoDB. We first went to these 2 because they're incredibly popular and we knew the sheer scale that they could eventually get to. Mainly as scale was the limiting factor for Elasticache. We wanted to make sure that we could future-proof our technology. Both of these also have use cases with well over 1,000 nodes, which obviously would very easily meet our future needs. They also had great support surrounding them, as Cassandra is an incredibly popular technology. It has a very large and active community, which makes getting any answers to any question incredibly easy. For MongoDB, we went with a company called ScaleGrid. They offer fully managed database as a service solutions. They as well also had incredible support. When we were doing our benchmarking, one of the solutions architects was essentially watching our benchmark every step of the way to make sure our database was as tuned as possible, giving us the best results for what we had. Unfortunately, where these 2 fell short was on latency, where Cassandra and MongoDB were seeing P95 latencies of about 13 milliseconds and 9 milliseconds respectively. And this was a problem. As Varun said earlier, we have multi-level calls. So each millisecond lost in latency would be multiplied 3 to 4 times. So losing upwards of 9 to 10 milliseconds on each call was simply unacceptable. They're also not too well suited for our use case, as we strictly are looking for key value lookups, and that just scratches the surface about what these technologies actually had to offer. And there's also a little bit of a learning curve along with that, as we'd have to be switching from Redis to an entirely new technology. There's a little bit of learning and some man hours that would have to go into actually learning how to manage these on our own. Next up, we went to Couchbase. We initially went to Couchbase because they were a great fit for our use case. They were strictly a key value, or strictly used for key value stores, where the value is in JSON, which is exactly what we were looking for. And our initial latencies were actually very promising. We were seeing about P95s of about 1 millisecond or so. So we weren't sacrificing too much on latency. Once again, there was also a great amount of support. They just so happened to have an office in Bellevue, Washington, which is roughly about 15, 20 minutes out of our office. And they actually offered to come meet up with us for lunch as we were doing our benchmarking, so they could personally help tune our database and give us the best results possible. One of the biggest, because of this, they actually passed our first round of testing. So we moved on to using real world, or our actual data at the exact scale that we were trying to use it at to see if we could keep up the same performance. Unfortunately, this is where some problems start to arise, as there is actually a minimum RAM requirement that Couchbase has. It requires all keys and all metadata, which is roughly about 50, 60 bytes of metadata per key, to be stored in RAM at all times. So that directly has an effect on cost, as there is a minimum amount of RAM we need to have on our cluster at all times. And because of that, our latencies actually started to falter at scale, as all the keys and metadata, that turns out to be a very large chunk of memory. And so we were seeing RAM hit ratios of 15, 20% when it came to actual full-scale testing. And that caused the latencies to falter a little bit. And because of that, we were just sacrificing way too much on latency to actually go with this solution. And in terms of cost, with this RAM requirement, we would have needed roughly about 25 i3 4x large nodes to host our cluster. And on top of that, we also had to, or would have had to gone with an enterprise solution to be able to tune our database to what they were telling us to do, which simply would have cost way too much for sacrificing a few milliseconds. In terms of using self-hosted Redis, we initially wanted to go with this solution, as it would get rid of the the restrictions that Elasticache gave us. We'd keep the same great performance. It was familiar technology, as we were already using Redis. But unfortunately, there was a little bit of management and stability issues when it came to managing a cluster of this scale. And just the flat cost of having to store everything in RAM. We would have had to keep the same 30 or so nodes, or roughly about 30 or so nodes for our cluster, which simply just was way too much. And that's what led us to learning about Redis on Flash. So some of the key features is that Redis on Flash has the unique ability to no longer be bound to storing all keys and values into RAM like traditional open source Redis, and allows for the use of flash storage to also store values and hot swap them in and out of RAM as needed. One of the key things that's incredibly nice is being able to utilize brand new NVMe SSD volumes, as this keeps everything brand new, the newest technology, and pretty much keep everything as quick as possible. It was also utilizing the node resources more, as we weren't just using nodes simply just for RAM. We were actually we were seeing CPU utilization of around like less than 1% when using Elasticache, as we had these beefy nodes literally just because they had RAM. And now we can actually use more of the node. We also saw significant cost savings. As flash storage is significantly cheaper than RAM, we actually cut our costs per gigabyte of data by close to 60%. And also in the same, along the same train of thought, the number of nodes was also decreased by about 40% in our cluster to host the same amount of data. And one of the great things is this required absolutely no change to our existing infrastructure, as we are already using Redis as our database. Because of that, it was incredibly easy to integrate into our existing infrastructure, because all we had to do is basically just swap out a config file once everything was loaded and ready to go. We decided to go with a fully managed solution, as that required no more extra man hours to kind of really deep dive in the technology, and pretty much also added to the cost savings. Yeah, question? Do you know what type of instance that we're using right now? Yeah. We're using i3 4x large nodes. With the local SSD storage? Yeah. And so, oh, sorry. Yeah. Sorry, what?
Most articles say this is much, much slower than using it on RAM. What have you guys noticed in your tests?
So Varun's actually going to talk about this in a little bit.
I'll be covering that thing, and it's a very good question. And that was the I think that's the reason that we were mostly interested and skeptical in the beginning, and we'll have some key learnings that we got. Kind of address your question there.
Yeah, so a couple more slides. Yeah, so let's see, where was I? And so with Flight Managed Solution, we actually saw an incredible amount of support like we did the other technologies. As all of our benchmarkings were going on and as we were trying to push this into production, me and Varun have had multiple email threads with our solutions architect on off hours of the day, on weekends, even I woke up in the morning to see,
Sunday night.
yeah, to see like 1 to 2 a.m. after on Saturday or something, wondering why they're still talking. But yeah, the amount of support was actually just incredible. And because we were sticking with Redis, we saw completely unchanged latencies. We were still seeing roughly about 0.1 milliseconds during peak traffic times, which is perfect, exactly what we needed. It's pretty much the best of both worlds. We got this cost savings we wanted and didn't sacrifice anything on latency. So now I'll hand it back to Varun.
Hey, thank you so much, Jason. So yeah, I'll be addressing some of the deeper questions there, some of the key learnings and cost structure and more of this. So I think this slide, much more beautiful graphics was covered in the previous keynotes where they were saying, so if you see this architecture here, the left side is Elasticache, Redis on Elasticache. I don't even want to go to the version of Redis they are running or those things I keep updating. And frankly, we're not too worried about the version of Redis because our use case is very simple. Get, mget, sget, set kind of thing. So, but what used to always, make me feel really bad was like there is a huge amount of cluster, which are replicas, which are just sitting dead, just waiting that one of the primary dies and I will come to alive. And we always hope that nobody dies. And as a result, that whole node is kind of just getting waste. It is like active-passive kind of replication. We have had, in the past 1 year, we had 2 or 3 times that we had a failover of one of the nodes. So when the node fails over, node goes down, cluster is smart enough, it auto-recovers within 40 seconds to 1 minute. And by the way, the last time we had it was for 15-minute downtime that we had. And unfortunately, we had absolutely no control. We raised a support ticket, everything, but it takes time because there are some underlying changes that happen. Master lives in different AZ, replica lives in different AZ. So it's some amount of time. So the failover happens. But for the time of failover, all the requests, all the keys which are stored in that shard get invalidated. We get failures for them. So that's kind of bad. Plus, if you guys are Redis geeks, if not already, Redis is mostly, it's a single-threaded architecture, and as a result, it's mainly, as Jason was saying, we mainly use the beefy nodes for RAM, not for CPU. So all these nodes that are so big, we were not having more than 0.25% CPU users in any of those. It felt really bad, so much of wastage. While Redis Labs architecture of Redis is really interesting. They have the shard model, where single node has multiple shards. So if you see the lighted bulbs, which are the white ones, are the active ones, and then the passive ones are this. So if the first node goes down, let's say the primaries of shard 1 and shard 8 and shard 10 was living in the first node, the request immediately goes to any other node which has got the replica. So practically, we don't have any downtime there. So that's a big thing. Plus, this multi-sharded node, which was covered much more better and technically in the previous keynote there, or before the keynote, it's using multi-threaded, so it's much better CPU utilization that is happening. That gives us much more, our ability to scale up has grown up much more because of that. Previously, we were limited to no more than 300 to 400,000 requests per second, and that's, again, we have gone a little bit higher, but we were always scared because what is going to happen? We are getting bottlenecked by the CPU. RAM is super fast, fine, but what do you do if network is super fast because those instances are on high network, but what do you do with this primary thing? Here, we are able to scale as high as 1 million requests per second without any problems. And as for the slides there, I think we could scale up much more higher, but I was just scared to do that. Okay. Some of the systems that you were talking about, the node types and our clustered setup, we are using a clustered deployment with 20 i3 4x large nodes. All these numbers are kind of like a little bit of magic number which is computed based on your throughput requirement and your RAM to flash ratio that you want. And Redis Labs gives you the number that, okay, you use 20 nodes of this type and we just use it. Client, this is one of the learnings, not directly related, but it's kind of very interesting. So when people are going for clustered Redis, the clients are not that mature still in the market, at least the JVM-based clients. So the most popular client, Redis, it's good, but it's got its quirks. We have several instances where it just lost connection and was not able to auto-connect and all. So we went with Lattice finally, which is kind of much more lightweight and very intelligent. So it's shard aware. It's AZ aware, so it goes to the AZ which is closest to it, and it does some wonderful things. Compression, another very interesting thing, as we're saying, like we have very small data sets, and we have like 5 million entities, but they're not 5 million unique names, they're not 5 million unique cities and states and all other things. So there is a huge amount of repetition in our data. So we use dictionary-based compression Z standard, which is a Facebook proprietary algorithm there, or open source, I'm not sure. And that gave us around 60 to 70% compression. Any other algorithm was not able to give us that level of compression. CPU utilization shards. This CPU utilization, as we spoke, is much better, so we can scale up much faster, much higher. Now coming back to your question about several articles, and we ourselves read a lot of them, and we were not too sure about how is Flash going to work. Thanks to NVMe, thanks to Redis Labs for using that, and we were just surprised. All our benchmarking while we were doing it, we never ran more than for 4 or 5 hours. So we used to get like RAM hit ratio was around, so our data, just to start with, 30% of our data is in RAM and 70% of our data is in SSDs, flash. So you would theoretically feel that we should get 30% RAM hit ratio and 70% should be like SSDs. So we calculated, and we were getting around 0.5 to 0.7 millisecond latency. And our average payload size was half a KB per value that we were getting. And as I said, we were almost hitting like 200 requests per second, 200,000 requests per second. So it was acceptable to us, not great, but previously we were having 0.1 millisecond on pure Redis, pure RAM-based Elasticache, but 0.6, 0.7 was not too bad, it was not a deal breaker for us. We said, okay, let's go ahead with that. It's okay. Initially, when the cluster comes up, keys are uniformly distributed across RAM and SSDs, so our RAM hit ratio was exactly 30%, then it trickle down happens, and what we discovered was really good. When we ran over 20 hours of benchmarking and production run or semi-production runs, all the hot data which was getting accessed more often went up to the RAM, and the cold data, like nobody wants to search about me, but everybody's searching on Jon Snow. So all the Jon Snows of the world went up to the RAM, and I went back to cold SSDs and NVMe, and I was comfortable in cheap storage. So if you see, for like 96, 98% of RAM hit ratio, only 4% of data is little slow, and on average, our latency was still 0.1 or around that. So we practically lost nothing at the application layer, and we saved huge amount of money. And we can talk more offline about, if you have more questions, Jason, Heather would be happy to answer some of those things and this. So, okay, I'll just stop a second here. Any questions here so far? Yeah. So we in our architecture we try to move. Yeah. Okay. Sorry. The question was, are we using one data center or multi-data center, and how does the cost go with that? So we very consciously try to move data as less as possible. Because there are fundamental, but again, it's specific to each business. Our business, we are okay. If you change your address today and we are not able to update the next minute, we are okay with that. So we have batch processes of moving data across data centers. We have most of our clients located in East, US West zone, so most of our data centers are here. We have data centers in US East, or making some services are there in East, some are not, based on our client and the latency requirements that they have. But as far as the solution goes, it enables us to do anywhere. We can actually go to Europe, we can go to Singapore, and it is not stopping us. It can just go. It's independent, absolutely isolated. So I'll let Heather continue a little bit on some of the business benefits that we got, because end of the day, all of us here, it's a business company. We are not a research company. We are not like, we are data for good, fine, we do philanthropy, but still, we want to have business.
Yeah, so I mean, at the end of the day, we were looking for this solution because we were outgrowing Redis on Elasticache. And in addition to that, we're also really expanding our enterprise pro offerings with taking on new international data, and we can really anticipate the growth of the data set over the next couple of years. So it was really critical that we were able to find a solution that really didn't impact the cost factor too much, because we are really going into emerging markets, and we're testing the market and trying to prove the value proposition of these international data sets with different customers and in different verticals. So it really was a huge ROI for us to be able to achieve this, and to be able to not only really increase the size of our data set and incorporate new international data into our identity graph, but to do that at a fraction of the cost was just, obviously my CFO was pretty happy about that.
Any questions?
How do you shard your data? Is it based on the names of people? Do you do it manually?
Very good question. So as I said, our keys are UUIDs, and it's uniform. So we just let's Redis shard it on its own. It doesn't matter to us. Yes. So it's not based on any routing key or any parameter or column. It's just random keys. And that's, again, one of the key decisions in our architecture, that we didn't want to have any kind of custom logic of sharding, because that keeps on changing based on priorities, based on what is the most hottest product that we want to support. So this neutral architecture helps us to... right now we have 160 shards, 18 to 2.
Yeah.
Yeah, so the way Redis works is we have to have a shard for both replica and primary. So we have 80 shards, 20 nodes, which have 80 shards, and 80 replica shards. Altogether, 160 shards.
Yes.
So as you're doing traversals, you'll be hopping around between shards?
So the cluster client is very intelligent. It knows about the metadata, the keys, and that's how the Redis cluster, if you just go to Redis CLI -C, which is the cluster thing, and you type for get X, you actually will see which node it's getting routed to. So all the nodes, I'm not 100% sure about the architecture. You'll find a lot of people to explain the internal architecture of Redis cluster client. We know the behavior part of it, which is every node knows about where the key lives, and it knows some kind of hashing that they do to find out which shard this data is going to live, and it is redirected to that node. So you can file your request to node A, and it will say, oh, your data is in node C, and it will auto redirect and get the results. So cluster client does that all the magic for you.
Okay, but if you're doing a lot of edge traversals,
Oh, okay.
then you're going to a shop and finding
Yeah.
things and then going to the next one.
Oh, I see. Yes, internally, yes, absolutely. And that's why we are very latency sensitive, that if there are more depths, and there are going to be no more than 3, but there are depths. So if the storage system is not fast enough to have negligible hop thing and all, we are going to suffer. As Jason was saying, each millisecond delay there translates 3 to 4 times in here, plus the network time and all that. Any other questions?
Just a quick question. Are these slides available?
I think so. I'm sure they should be. Otherwise, feel free to just talk to one of us.
He's nodding yes. So.
Oh, it's there.
Yeah.
Okay. Okay, great. Thank you so much, everybody. Oh, sorry. Yeah, I think it's okay.
I was going to say, obviously, Titan has a very rich query syntax. You can
Yes.
express quite complicated graph traversals. Did you end up building something similar, or did you have a very, very simple
Yeah, very good question again. So as we identified our particular use case, that's what we try to encourage, like simple and frugal architecture. It's like Cypher or any other query language that you're using for Titan or anything and all, they try to cater to huge amount of use cases. They tried, like one of the keynotes again, they were saying like, how do we do aggregation better? So use that data structure and this. Every tree that you use or every data structure choice that you make has some downside on something else. And so we chose to write a very simple shape language, which we showed, which has no fancy features and way more simple to parse than any other language.
But our use cases for both our consumer and our pro customers are very well known and very well understood. So we were able to really introduce that simplicity.
Thank you, everybody. It was a great audience. Thank you.